Okay, this is where we left off last time. We were looking at the equation and we were saying that delta G equals delta H minus T delta S. And what we did was we were able to take the second law of thermodynamics and convert it into an expression that is related to properties of the system. Delta H is the enthalpy change. Remember, it's mainly for a chemical reaction, the net heat exchange at constant pressure between the breaking of chemical bonds in the reactants and the forming of chemical bonds in the products. And delta S is the entropy change in the system specifically. T is the absolute temperature. So mathematically, we said that if delta G turns out to be negative, in other words, if there is a net release of free energy, the reaction is spontaneous in the forward direction. So let's look at some things here with this. And let me get my pen and my highlighter. So the first thing we're going to do is, how do you calculate delta G? There are two ways. Obviously, if we have the enthalpies of formation and the entropies of the reactions, we can calculate delta G at a given temperature. But there's also thermodynamic data that you can find in that appendix 4 in your top hat, remember? Where you can find the standard free energy of formation, which is the free energy change that occurs when 1 mole of the compound is formed from its elements in their standard states. This is very similar to the way we calculated delta H. We invented a path where we took the reactants, we broke them down into their component elements, and then we took those component elements and built the products from scratch. So what we can find is that, for example, for any element in its stable form, delta G is going to be 0, just like delta H of formation is also 0. And so what we'll do is we'll calculate the standard free energy of the reaction. The reaction will undergo a free energy change when it occurs under standard state conditions. And I've been using that phrase standard state. We'll talk about it in a couple of moments. This is similar to what we did with delta H. Let's say that I have a prototype chemical reaction where the capital letters represent the formulas of reactants and products, and the smaller case letters represent the lowercase letters represent the stoichiometric coefficients. We would invent a path that takes us from reactants, deconstructing them, and building the products from scratch. So you would have essentially the negatives of the standard free energies of formation of reactants and the actual standard free energies of formation of products. So when you add all that up, essentially we're talking about the summation of delta AG of formation of products minus the summation of delta G's of formation of the reactants. And that is essentially what we're talking about. Now, before we do a practice example, like I said, we've been mentioning this standard state stuff here, right? Standard state. And I think it's important to review what that is. You would have studied this in Chem 1A, and I may have or may have not mentioned it when we studied delta H, I'm sorry. So here are the conventions for standard states. The idea is that if the substance is in the form of a gas, it's going to be at 1 atmosphere pressure. If it's in the form of a liquid or solid, it's going to be the pure liquid or the pure solid. If it's an element, it's going to have a delta G of formation of 0, but that only applies to the most stable allotropic form. Do you guys remember what allotropic means? No? An allotrope is the same element, but arranged in different forms. For example, oxygen can exist in the form of O2, the common diatomic molecule of oxygen, or it can exist as O3, which is ozone. The more stable of the two, I'm sorry, is the oxygen O2. Similarly, carbon can be graphite or it can be diamond, but the more stable allotrope is the graphite form of carbon. And for solutions, we assume the standard state to be a 1 molar concentration in the solution, okay? Just remember those things. These are the conditions under which you get the values of delta G of formation. And notice that we typically do it at 25 degrees Celsius, not at 0 degrees Celsius. Okay, let's do a little practice exercise here. What is the standard free energy change for the following reaction at 25 degrees Celsius? Now, just from looking at it, you should be able to identify what kind of reaction that is. Okay, by this point in time, you should be able to identify just from looking at the chemical equation. Yes, this is a combustion reaction. The compound that we are burning here, although it's not specified, is actually benzene, C6H6. So again, let's go over our strategy. Remember, to calculate the standard free energy change for the reaction, or the standard free energy of reaction, we have the products minus reactants. Let's see what the products are. We have CO2 and we have H2O. Got to be careful because the H2O here is liquid. And we have to take whatever the standard free energy of formation is, multiplied times the stoichiometric coefficients. So we had 12 times delta G of CO2 plus 6 times delta G of H2O minus 2 times the delta G of benzene. And again, remember that the oxygen would have an delta G of formation of 0 because that is its most stable elemental allotrope. So now it's a matter of finding the values. By now you remember that we said that you're gonna find this in appendix. Oops. Okay, I can do this. Okay, I guess this guy is not working. Let's try the highlighter. Okay, so appendix 4. That's where you're going to find these things in Top Hat. It may be actually that the values that I'm going to put in here are not exactly the ones in there. I may have gotten these from a different source. Always remember, whenever you get these numbers, there's going to be some variation depending on the source. So CO2 is minus 394.4 kilojoules per mole. Water liquid is minus 237.1. Benzene is 124.5, which gives me a total of negative 6,404 kilojoules per mole. At least that's what I have here. Okay. Couple of things I want to ask. First of all, is this reaction spontaneous at 25 degrees Celsius? Remember the criterion? What is the value of delta G for my system, for my reaction? Negative 6404 kilojoules per mole. In other words, it is negative, right? And we said that for a process to be spontaneous, delta G has to be negative. Therefore, this process is spontaneous. But we knew that, right? Because we said, well, it's a combustion reaction. Combustion reactions are spontaneous. All you have to do is give it a spark, bang, that thing takes off and burns all the way down. Burn, baby, burn. But let me ask you this. If you were to look at the equation here, let me erase this thing out of here. Let's count the number of moles in the products, the number of gas moles in the products versus the number of moles of gas in the reactants. Okay, you'll notice that the change in the number of moles of gas is negative, right? In other words, wish I could get this thing to work, but it's not working today. What happens when you have a reduction in the number of moles of gas? What happens to the entropy? That's right. The entropy of this process should be negative. There should be a decrease in entropy because you're going from more moles of gas, 15, to less moles of gas, which is 12. But our delta G came out to be negative, right? So therefore, since the temperature is relatively low, 25 degrees Celsius, which property then is driving the spontaneity of this reaction? That's right. This is a very exothermic reaction. And it is that enthalpy function that is driving the reaction. In other words, the tremendous amount of heat released causes the surroundings to increase in entropy and therefore offset the decrease in entropy that our system is going through. All right? That's the way I want you guys to think. Okay, I'm gonna skip a couple slides ahead if you don't mind. I'm gonna jump over to, I don't know what number this would be, 42, 43. Just wanna give a quick review here, right? Remember that we said for the second law of thermodynamics, I hope you've located this slide in your handout. What it says is that for a process to be spontaneous, there has to be an increase in entropy of the universe, increase in entropy of the universe being composed by delta S of the system and delta S of surroundings. Now, we also said that for the process at equilibrium, delta S of the universe equals 0. Then what we did was we built a system at constant temperature and constant pressure. And we said that for that system, we defined this change in free energy, right? This gives free energy, which is like saying this is of all the energy transactions that happen in the process, this is what would be available to perform productive work. And we said that if delta G comes out negative, the reaction is spontaneous in the forward direction. Delta G is positive, the reaction is non-spontaneous as written, but it means that in the reverse direction, it would be spontaneous. And if delta G equals 0, the reaction is at equilibrium. So delta G equals 0 would be kind of like the turning point where you could go from spontaneous to non-spontaneous. And in light of the discussion we just had a few moments ago about delta S and delta H and the relative contributions, I'd like for us to look at this table on the next slide. Here's the equation in the top. And remember, our goal is for delta G to be negative. So what we're going to have to do is we're going to have to compare the relative effects of delta H, delta S, and the temperature. So I have 4 scenarios here. Let's start out with delta H being negative, delta S being positive. Notice that if delta H is negative and delta S is positive, that means that the second term in that equation, the minus T delta S, is going to be negative because delta S stays positive. It doesn't cancel out the negative sign. And if delta H is negative, that means that at any temperature, this reaction will have a negative delta G. In other words, it will be spontaneous, like we see there in the first case. All right? All right, let's look at the second scenario here. Let's say that delta G delta H, I'm sorry, is positive. And let's say that delta S is negative. That's the second case. Notice that when delta S is negative, that means that minus T delta S becomes positive, right? You're going to add T delta S to an already positive delta H. In other words, there is no value of temperature for which that equation is going to give me a negative delta G. And so as the second line on the chart says, under these conditions, the reaction will be non-spontaneous at any temperature. And you can see some examples there on the right. All right. Now, let's go to the third scenario, and now we're going to encounter some interesting issues here. What if both delta H and delta S are negative? It's the third scenario. Okay, notice that that means that delta H being negative, it's fine. It's the second term that worries us because you're subtracting a negative number, which means that double negative converts into a positive. So that means that the first term, the delta H component, is going to be negative, but the second term is going to be positive. So it's all a matter of when you add them up, who wins? Well, what determines who wins is the temperature. Notice that if the temperature is small, if it's low temperature, then if you look at the absolute value of the second term there, you're going to be adding a small number to an already negative delta H. And so as you can see here in this case, that means that you'll get a net negative delta G. The T delta S term is not going to offset the negative delta H. So the reaction will be spontaneous at low temperature. At high temperature, though, what might happen is that that second term becomes significantly larger. And since it's coming in positive, it might offset the delta H value and turn the reaction into a non-spontaneous range. So you can see, for example, the freezing of water. We know that if you want to freeze water, you have to do it at low temperature, right? Water's not going to freeze at 60, 70 degrees Celsius, but it'll freeze at zero at low temperature. And you can see where at a low temperature, the process is spontaneous, even though it proceeds with a decrease in entropy. Remember, the liquid to solid transition decreases entropy. Okay, let's look at the other case here. So this is going to be the case where both now inverted. So now delta H is going to be positive. Man, I can't get this thing to work. Come on, buddy. Help me out here. So here delta H is positive and delta S is negative. Gosh. I think I know what it is. I need to clean my screen. That's what it is. So if delta H is positive, that means that that side of the equation is not favoring spontaneity. But since delta S, I'm sorry, it's also positive, I'm sorry, that side of the equation is going to turn negative. So once more, at a low temperature, the T delta S component is not sufficient to offset the positive value of delta H. And as a consequence, you can see here where delta G stays positive and therefore the reaction is non-spontaneous. However, at high temperature, that T delta S term becomes larger and it might be able to offset the positive delta H and turn delta G negative, which will mean the process will be spontaneous. So you can see in the case of the vaporization of water, of course, we know that at low temperatures, it's not going to happen, or at least not perceptively. But at high temperatures, closer to the boiling point of water, 80, 90, 100 degrees, that process will be spontaneous. Okay, so I want you to look at this table, maybe make a copy of it, memorize it, or if we end up having a cheat sheet in our next exam, this definitely is a candidate to be on that cheat sheet. All right. All right. So with these ideas in mind, let's go back to a few questions we had way in the kind of like a little while ago. Let's look at the equation again. Can a process be spontaneous if it's endothermic? Remember that we thought that if the process costs more energy than it yields, and therefore you have a delta H deficit, the process could not be spontaneous. However, we saw that, for example, the melting of ice is endothermic, but at the same time, it's also spontaneous. So once more, remember, if delta H is positive, what can happen that makes the process spontaneous? Right, look at the table we just did in the previous slide, and you'll see that, yeah, if the T delta S term is larger than delta H, in other words, if the temperature is sufficiently high, then it'll turn the equation back towards the negative. Second question. Can a process be spontaneous if delta S is negative? In other words, if the system undergoes a negative entropy change. Well, first of all, remember that according to the second law, there's nothing wrong with that. The only thing that has to increase is the entropy of the universe, right? And we just saw that if delta H is negative, in other words, if the process is sufficiently exothermic, mathematically, that negative delta H of the system on the equation offsets the positive that you're going to get from that T delta S term, and therefore you end up getting a net negative delta G. But also remember that a negative delta H, in other words, an exothermic process, typically causes the entropy of the surroundings to increase. And it may be that the increase in the entropy of the surroundings offsets the decrease in entropy of the system. So you can argue, in other words, this mathematically based on the equation, or going back to what we discussed about system versus surroundings. Now, this is a very important one. If delta G comes out to be negative, does that mean we'll be able to observe the reaction happen? That's right. Delta G being negative just means that the process is spontaneous. It doesn't mean that it's fast. Remember, whether you can see a reaction happen or not is an issue of the rate of that reaction. And the rate of reactions is kind of part of the realm of chemical kinetics. All right. So be careful that, again, like I said before, don't get mixed up between something that's spontaneous and something that's instantaneous. Here's another thing that might be good to keep in mind. And again, as you go through these things and you do calculations, trends begin to emerge and you can spot certain trends. We talked about the trend of entropy change when there's a change in the moles of gases. Entropy changes when it's a physical state change, a transition. There's also a trend when you look at reactions in solution. And a lot of our reactions that we carry out are in solution, acid-base reactions, reactions of a metal with an acid solution, precipitation reactions. A lot of reactions, we do them in aqueous solution. Well, it turns out that in many reactions in solution, the delta H alone is a good indicator of whether the reaction is spontaneous or not. In other words, in this particular category, yes, a negative delta H goes with a spontaneous process, and a positive delta H goes with a non-spontaneous process. Remember that we said that that doesn't always hold true, but in reactions in solution, most of the time, delta H by itself is a good indicator. Now think about it. What is the entropy change if a reaction is carried out in solution? What is delta S of the reaction? Well, remember, the entropy of a system in solution is already fairly high. We said that when you dissolve a solute in the solvent, the entropy increases. So you're already at a fairly high level of entropy. And so the entropy change that happens during the reaction is not going to be that significant. And so delta S is going to be nearly zero, meaning that in the equation, delta G is approximately dependent just on delta H. Like I said, this is not true in all cases. It's just a trend. For example, you could think that in a precipitation reaction, delta S is significantly negative, right? Because you are going from the system, the substances in solution, to now a substance that's a solid. So, like I said, it's just a trend. It's a good indicator in many reactions, not in all of them. Okay, I think we're ready for some other concepts here. What about transition changes, phase transitions? Let's consider, for example, the vaporization of water. Remember that when a liquid converts into its gas state, initially the rate of vaporization is greater than the rate of condensation, or vice versa, if you start, one order. So let's say, for example, that I am going to track this over time. And let's say that I started out vaporizing the water. And as time went on, the rate of condensation started increasing until you arrived at this dynamic equilibrium. Remember, where you have equal rates going forward and going in reverse. Now, equilibrium in terms of free energy change has a specific value, right? Since the boiling of water, the equilibrium of liquid and gas water happens at 100 degrees Celsius, then at that temperature, the system is at equilibrium and therefore delta G equals zero, right? We said that at equilibrium, a system equals zero, and the boiling point represents a system in equilibrium. Okay, let's put in our equation, and what we're going to do then is let's rearrange this in terms of delta S. What would be delta S for this process? Well, let's simply rearrange. We're going to take the T delta S on one side, divide by T on both sides, and now we get delta S equals delta H over T. And since this is the process at equilibrium, this delta H is specifically the heat of vaporization of our system, all right, which we can get from tables or from Google. So let's say I want to calculate what is that. If I look up the value of delta H of vaporization of water, it runs usually in the range of 40 to 40 something kilojoules per mole. Oh, this is very exact here. 40.79 kilojoules per mole. That's very precise. And of course, at 100 degrees Celsius, that's about 373 Kelvin. I'm surprised I didn't put 373.15 Kelvin. Gosh. So if we solve that, we see that this comes up to be 1.09 times 10 to the minus 1, or 0.109 kilojoules per Kelvin per mole. Yes, it's a positive change in entropy. It's about 109 joules per Kelvin per mole. And as you can see, typically, entropy changes are not very large. That's why we typically express them in joules per Kelvin per mole, whereas enthalpies are expressed in kilojoules per mole. All right, so this is 109 joules per Kelvin per mole. So it is positive as we expected because we're going from liquid to gas. But as you can see, that's the value that we get. All right. Now, let me ask you this. let's say that we look at not the vaporization of water, but the melting of ice. In other words, the transition from solid to liquid. Would you expect that process to have a larger, same, or smaller delta S? In other words, a smaller, equal, or larger entropy change. Well, it should be smaller, right? Because remember, the transition from liquid to gas is a transition to a myriad of microstates in the gas state. Transition from solid to liquid, yes, it increases entropy, but the entropy of liquids is not that huge, right, compared to what it is for a gas. And so that'll be a smaller entropy change. Actually, I think it's somewhere in the range of about 20 joules per Kelvin per mole, like a fifth of what it is for the vaporization of liquid water. All right, are you guys ready to do a little practice exercise here? I think you are. Let's go ahead and do a little practice here. Let's go to the next slide, and I'm going to switch us over to our see, I can switch us to our I can. Okay, guys, we're gonna have to take a break here because my connection has gotten very poor and I can't seem to get this guy. Or wait a minute, maybe I can get it. Ah, there you are. I got it. Everybody seeing that? All right. So let's put in that slide that I just showed. It's this guy. Let's see if I can zoom in a little bit. There we go. So here are two reactions. They don't tell us what the reactions are. They just tell us what the value, the thermodynamic values are. So let's say these reactions are being carried out at 25 degrees Celsius. And given the values of delta H and delta S, is either one of them non-spontaneous or non-spontaneous? And if it is non-spontaneous, can we adjust the temperature to make it spontaneous? Ready? Let's do this. Okay, so remember, let's go with reaction A. Remember, delta G equals delta H minus T delta S. Having a problem with my connection here. So let's see what it is for this first one here. All right. So in this case, delta G would be delta H 10.5 kilojoules per mole minus T, but remember we had to use Kelvin here, right? So 25 degrees, about 298 Kelvin. And it says the entropy change is 30 and that is joules per Kelvin per mole. But because enthalpy was in kilojoules, we had to convert that. So 1 kilojoule is 1,000 or 10 to the third joules. So that'll cancel out. And Kelvin will cancel with Kelvin. Let's do the math. And this comes up to be like 1.56 kilojoules per mole. Is it spontaneous or non-spontaneous? Right, this is positive. In other words, this is non-spontaneous. Now, can we find a temperature at which we'll turn it around and make it a spontaneous reaction? Well, remember, the turning point would be the temperature at which delta G becomes 0. In other words, it switches from non-spontaneous to spontaneous when it reaches equilibrium. So our turning point would be at delta G equals 0. And remember, when delta G equals 0, basically we have, delta H minus T delta S. I want to find out what is the temperature at which that will happen. So I'm going to solve this here. I'm going to rearrange this, and this would be a temperature at which delta H over delta S equals T. So this one we said was 10.5 kilojoules per mole. And delta S was 30 joules per Kelvin per mole. And we got to convert to kilojoules, right? So 1 kilojoule, 10 to the third power joules. So we got the joules cancel out. We got the kilojoules cancel out. The per moles cancels out. The kelvins are going to flip up. So we got a temperature. And so this will be about 350 Kelvin. So that means that above this temperature, the reaction is spontaneous. Now remember, 350 Kelvin is really not that bad, right? It's not a hugely, incredibly high temperature. Okay, let's look at the second one now. Let's look at reaction B. You know, let's do chemistry before we do math. Notice the following. Delta H is positive. Delta S is negative. We just went through this scenario, right? So there's no need for us to calculate this. We know that with a positive delta S, for the positive delta H and a negative delta S, this is always going to be positive. In other words, delta G is positive at all temperatures. No need to do any calculations because that was not the question. The question was, are these reactions spontaneous? No, delta G is positive. So in other words, let me just write down here, non-spontaneous. At all temperatures. All right, let me leave that there for a few moments. You guys can write them down. Let me see, I can squeeze this out to the right a little bit so you guys can see it. All right, so I'll leave that for a few more moments there. We're gonna take a break in a few moments.